Welcome back to our podcast. This is Dr. Edward Ngwenya, and we will be talking about lasers. We'll be tackling the subject of lasers in this podcast and just giving a succinct overview of what lasers are, how they function, the physics therein, the types of lasers that we get, and the uses thereof. So it will just be a brief overview on the subject of lasers. Now, lasers can be something that, can be a bit tough to understand, but it's actually easy when you break it down. Now, in order to understand what laser is, and I would suggest that you listen to this podcast in conjunction with the podcast that we did on radiation, because you'd have an understanding of the electromagnetic spectrum. Now, let's remember we've got the electromagnetic radiation. And along or throughout this radiation spectrum, if one may say, we've got different portions of radiations in there. Now, we've got light. And what is light? Light is the visible portion of the electromagnetic radiation spectrum. So what we can see, and as you know all the colors of the rainbow. You can see from red all the way up until violet. It's red, orange, yellow, green, blue, indigo, and violet. So that is light. That's how we define light, the visible portion. Now, this portion is also defined by the wavelengths, because what gives us the colors will be the wavelength in which this radiation travels. So red, you're looking at about 700 to 750 nanometers, and all the way up until violet, where we look at around 380 to 400 nanometers, oddly there. Now, anything from violet going up is ionizing radiation. That's what we call ionizing radiation. And anything lower down from red going lower down there, but with the wavelength, of course, higher up, would be non-ionizing radiation. Now, remember, when we looked at radiation, we spoke about from violet, we went to ultraviolet. And ultraviolet are those UV rays that we get from the sun. Remember, for the sun, we get infrared, which gives us warmth, we get light, and then we get ultraviolet rays, which are UVA and UVB. But the Earth, actually, the astral, what can I say? The ozone layer. It absorbs anything greater than 290 nanometers. And so we only able to get through UVA and UVB. However, there's also UVC, which does not get through. After ultraviolet, we get X-rays, which is 10 nanometers to 0.01 nanometers. And then we get gamma rays, which is anything from 0.01 nanometers going forth there. And remember, as we said, this is ionizing radiation destroying DNA. Now, where we are going to focus on is on the other side of the spectrum, because that's where we use our laser. So remember, anything then from red, when we go lower down, it's infrared. So infrared, we're looking at about 750 nanometers to 1 millimeters. From infrared, we have microwave. Microwave, 1 millimeter to 1 meter. And then we'll have sound. Sound from 1 meter to 100 kilometers. And of course, sound then, will be differentiated to ultrasound, to acoustic, to infrasound, depending on the hertz thereof. We know whatever is audible is anything that's greater than 20 kilohertz to 20,000 kilohertz. This is acoustic sound that we can hear. Now, what is laser? Laser, as the word is, it stands for L, light amplification by stimulated emission of radiation. This is what we're going to break down. Now, what it's important to understand as compared to light is that laser is a source of coherent monochromic radiation, and so it's specific to this electromagnetic radiation, and I'll explain what I mean by that. So what we do, we take light and we amplify light. So you'll have an energy source, which is light, a light source, and we amplify this light. How do we then amplify this light then? It goes through stimulated emission. So generally what we have naturally occurring, if you look at the photons and electrons, we have spontaneous emission and spontaneous absorption. It's just unfortunate through the audio, it's difficult for me to explain it, but it would be better graphically. But what you would generally have is in the middle, you have this positively charged proton and this electromagnetic field around it with a stable, metastable, and excitable state in which the electrons would then go up and down. And generally in nature, you get this these electrons moving from a metastable to excitable to a stable state through this spontaneous emission and spontaneous absorption. Remember, I'm going to try to stay high level. It gets a bit technical, but I just want you to understand it at a high level. I don't want to overcomplicate it for you. But so what we then do is that we through using this light source, we then excite this electron from a metastable state through to an excitable state, and the way it flows as we excite this, it then moves from an excitable state back to a stable state. But what can I say? But it's as it does that, it will then take out, or rather elicit, a radiation force or a radiation, a certain emission. It will stimulate a certain energy that would then go out of the source. As I said, it's a bit technical, very difficult to explain it with you without a drawing, but generally what would be easy for you to understand as I'm explaining to you, I would be happy if you can just understand that we take this light source and we take it and it's basically, we then stimulate this emission of radiation, and through this we then get a coherent monochromic radiation wave that will then form versus light, which is then scattered. I hope this makes some sense, but it would serve you, quite well if you could go back just to the physics thereof and just read and understand, see the pictures, see what they look like. And subsequently, I've actually got a video where I give a lecture just explaining, and we show you how this current then comes in and excites these electrons, and then the energy that then is exhibited from then going forward. So in laser, what are a requirement for a laser when we speak of laser? So when we speak of requirements, what we need first, as we've mentioned, is a source, an energy source. This can be either light or electric source. And then we will then have a medium, or rather an oscillator, wherein we will then insert a medium in which we will then generate this energy and this radiation field throw in, where this process of stimulated emission will then take place. And the type of medium that you use is what's going to define the type of laser that we have. Now, we also then, in this laser that we are making, we've got our energy source, we've got our medium. Now, between the energy source and this medium, we'll then have a full rear reflective mirror, 100% reflective mirror. And then in front of this oscillator, we'll also have another reflective mirror. Now, this is important because when we excite these electrons, we will then have a certain radiation and energy that then forms, but these waves will generally be small, but we want to combine these waves. And so we combine them through these reflective mirrors that then go and oppose each other, creating this larger waveform that will then go out to then meet this optic lens and then go towards the patient. As I say, very difficult for you to catch through an audio, but it's important to go and look at it, look at the diagrams and have a look at my lecture that I give where I show these phases. So we've got an energy source, we've got a medium, and then we've got reflective mirrors and optic lens that we then have, and some lasers, as we will speak going forward, will then have other factors such as a Q switch, which will then elaborate further on. So now we speak about this medium. What type of mediums can we use? Now, we can either have a solid medium, a gas medium, or we can use liquid as a medium. So what types of liquid can we use? We can use, when we use liquid, we can have things like dye lasers. When we use gas, we can use things like argon. We can use CO2. We can also use carbon monoxide, CO. We can also use krypton, which is one of the lasers, as we'll speak about, that you'll start to understand. And then solid mediums that we use, generally we'll use like neodymium, or we'll use iridium, ruby, alexandrite. We can use what we know as YAG, which is yttrium aluminium garnet. So these are the different types of mediums that we use. And depending on the medium that you use, that would be the type of lasers that you will have, generating a certain wavelength that you will then use, which will have a specific function, as we will now find out. So how does this laser then work on the tissues? You see, laser can either be, or the effect on the tissue can either be, it can either be reflected, it can either be transmitted, it can be scattered, example, shorter wavelengths, or it can be absorbed. And generally, the effects that we then have will be one of three. They can be thermal, they can be mechanical, or they can be photochemical. Thermal, mechanical, or photochemical. Now, thermal, we can divide into three. Anything around 60 degrees Celsius, thermal, it can be, through coagulation. Especially, things like proteins, we get coagulation. So laser, the effects, it can denature tissue through this coagulative process. Vaporization is one of the other effects. Generally, when degrees are about 100 degrees Celsius. And what we generally then use Another which I want you to know about is selective photothermolysis. That's the specific one. Selective photothermolysis. Now, what is that? In that, we target a specific chromophore. So, depending on the wavelength that is being emitted, a specific chromophore will be targeted. And it's important for you to have a look at the diagram. There's actually, you will see a table where you would then have these wavelengths and the three specific chromophores that are there. It's water, melanin, and hemoglobin. But just on an overview, and I'm giving just a general overview because they overlap and it's specific when you look at the diagram. Generally, hemoglobin will be affected by, wavelengths of about 500 to 600 nanometers. Melanin, you're looking at about 600 to 1,000 nanometers. And water, anything greater than 1,200 nanometers. By the way, as I mentioned these are just a wide overviews, call it, broad spectrum figures that you can use. However, the diagram would be able to specifically show you which chromophore is affected on which wavelengths. With mechanical, of course, we've got cavitation and we've got shock waves that then form, just for you to remember that on that side. Now, what do I want us to now know? Important things for you to know about lasers will be, the next thing would be the type of lasers. And how would you classify then these lasers? Remember, we spoke about the medium that you use. So the mediums will tell you the type of laser that you use. The way we classify them based on, are they ablative or are they non-ablative? Ablative versus non-ablative. So, ablative lasers, generally there are two main lasers that would fall within that category. That would be our CO2 lasers, and that we are looking at, wavelengths of about 10,600 nanometers. And then you've got your iridium YAG lasers. This being your iridium yttrium aluminum garnet lasers. That's about 2,940 nanometers. Those are ablative lasers. And the chromophore generally, specifically, that they would target would be water. And the uses that would then use those ones would be more on skin resurfacing and the rhytids, as you would see them. We'll speak about those a bit later. Then we've got our non-ablative lasers. Now, these are our, we can put our ND-YAGs. Remember, we spoke about ND, which is neodymium. And YAG is yttrium aluminum garnet. So you can use ND-YAGs. There's a newer one where we've got about 1,320 nanometers. So we put that in our, ablative side. But generally, our ND-YAGs that we had were about 1,064 nanometers. We do have the KTP ones also with the KTP crystals, the ND-YAGs, which would give you a wavelength of 532 nanometers, which is generally half of the 1,665, the ND-YAG with the Q switch. And so then the other ones that would have are your alexandrite, that's about 755 nanometers, your ruby, which is 694 nanometers, that's with a Q switch. Then the krypton, which is 647 to about 676 nanometers. And then we then have our pulse dye, lasers, which are lower down in nanometers, 500 nanometers are the figures you would get on a wavelength. And then a special one I'm going to put on the side, which is not a laser. As we've mentioned, remember we defined what light is. So this uses a greater spectrum of light from 510 to 1200 nanometers. This is our intense pulse light, our IPL, not a laser. Remember, as we've mentioned, the wave form is not coherent. It's not monochromic. So it's important though to know about IPL in this part and be able to differentiate it from a laser. Now, the ones that would target hemoglobin in these are generally our pulse dye lasers. That usually is hemoglobin, or our Nd:YAG, which is the one with the KTP crystals, the 532 nanometers. Those would generally target hemoglobin. And these are the ones that we'll use on our vascular lesions, our port 1 stain, telangiectasias. Those ones are the ones that would be used there. And then there would be the ones that then target melanin. Remember, we said melanin generally between 600 to 1,000 nanometers. Now, those ones would be now our krypton, our ruby, our alexandrite, our Nd:YAG, the 1,064 nanometers. So these would target melanin as a chromophore. And these generally we use, for pigmentation, lesions or areas. Tattoos are big ones, yellow, white, usually being the most difficult raid to remove the tattoos they're in. But those are the ones that we would use for melanin. And as I mentioned, our ablative one, CO2 lasers, ER-YAGs are generally for water and would use those more in our skin resurfacing. Things to know: pulse versus continuous are things that maybe we must just know. Generally, we may use pulse just to limit the effect on targeted chromophore, basically without affecting the surrounding tissue. And these are things like your Q switch. So what it does, it generates this, you call it this electromagnetic radiation energy within this medium, kept within these reflective mirrors. And then just, you think of it as, filling a tub with water. You fill the tub, you fill the tub, you fill the tub. And then what you do, you remove the entire floor or bottom of the tub at a go, and all the water goes down. At a go. That's how a Q switch goes. It fills up, it builds up, it builds up, and then you remove that bottom of the tub at a go, and then it gives that one blow, directed to that chroma floor. So that's how I can explain how Q switch would then work. Another important thing, basically, that I would like you to know, maybe lastly, is laser safety. It's important to know it is regulated. And those are based on the class levels from 1 up until 4. And you'd need to know class 1, which lasers can you use, usually in enclosed areas. Those are safe. Class 2 are low power lasers. Class 3, they would require specific training and they can cause usually damage, like your Nd:YAGs. And then class 4 are, these are most of the medical lasers, and they require specific safety measures. You need special eye protection, storage of a key, fire protections, control area. A patient would need to have no jewelry. All these different areas. It's something important just to know in terms of laser safety. So I think succinctly that's a summary. I think I'm happy if you can just capture that about lasers. Just know what a laser is versus what light is. Also know what laser stands for: light amplification by stimulated emission of radiation. Just have a little understanding of what stimulated emission is. have an understanding of what the requirements of laser are, the light source, the medium, the reflective mirrors, the optic lens. Just have a, just a brief overview on the effects of a laser on tissue, the thermal effects, the mechanical effects, the photochemical effects, and most importantly, within the thermal effect, the selective photo thermolysis. Know about the targeted chromophores, know about the wavelength specific to those, and then just have an understanding on the way the type of lasers that would target specific chromophores that we would use. And I think that I would be happy with, and maybe the safety standards of lasers, the complications and the contraindications of lasers. And that should put you high up with the A-class students when it comes to understanding lasers. I thank you for your attention. Look forward to chatting next time with you, as we'll be tackling more and more of these plastic surgery topics and getting a better understanding of them. The point therein is that you have read, you've got a basic understanding, and these are just to enhance and to add to that understanding. Thank you. Take care. Bye bye.